The only surface forces acting in the x direction on the control volume of figure 12.1b are due to pressure. The infinitesimal upper and lower areas have zero friction because we assume the wave is one-dimensional. We have derived an expression for the speed of sound in any medium in terms of thermodynamic quantities. Equation 12.15 indicates that the speed of sound depends on how the pressure and density of the medium are related. To obtain the speed of sound in a medium, we could measure the time a sound wave takes to travel a prescribed distance, or instead we could apply a small pressure change to a sample measure, the corresponding density change, and evaluate from those. There is only one problem with equation 12.15. For a simple wave, by definition, we have an infinitesimal pressure change, i.e., it is reversible, and it occurs very quickly. So there is no time for any heat transfer to occur, i.e., it is adiabatic. Thus, the sound wave propagates isentropically. Hence, if we express P as a function of density and entropy, P equals then the following formula. We can now apply to solids, liquids, and gases. For solids and liquids, data are usually available on the bulk modulus E, which is a measure of how a pressure change affects a relative density change. For these media, an ideal gas, that is, the pressure and density in isentropic flow, are released and related by an ideal gas. The speed of sound in air has been measured precisely by numerous investigators. The results agree closely with the theoretical prediction of equation 12.18, which is that the speed of sound is a function of temperature only. The variation in atmospheric pressure or temperature with altitude on a standard day was discussed in Chapter 3. The properties are summarized in Table A.3. The corresponding variation in C is computed as an exercise and plotted as a function of the altitude. In this respect, this example illustrates the relative magnitudes of the speed of sound in typical solids, liquids, and gases. Do not confuse the speed of sound with the attenuation of sound, the rate at which internal friction of the medium reduces the sound level. Generally, solids and liquids attenuate sound much more rapidly than do gases. Flows for which m equals subsonic, while those with m+1 are supersonic. The flow fields that have both subsonic and supersonic regions are termed transonic. The transonic regime occurs for Mach numbers between about 0.9 and 12.1, although most flows within our experience are subsonic. Hello? Yeah. Yeah. Okay.